No, it's not this one. Hello, everyone. My name is Peng. I'm from University of Arkansas, Lawrence Group. I'm a postdoc working with Professor Balash. Today, I would like to present our recent work about light-assisted creation and control of novel ferroelectric materials. This is a cooperation work. So many co-authors. For instance, we have Charles from France, Changsong, Bin, Hongjian from China, and also Hockey from Luxembourg, Sergei Yusoro and Laurent from the University of Arkansas. First of all, I would like to acknowledge all the fundings. So the work has mainly been supported by Office of Naval Research, Department of Defense, Army Research Office, and all the numerical simulations were performed in the Arkansas High Performance Computing Center. So light. So what happens when light interacts with materials? And studies have shown that light can be used, for instance, like a tweezer. You can use light to move some atoms or nanoparticles. You could also trap some molecules or nanoparticles by some optical trapping. If there are multiple of laser pulses focused on a small portion of this material, and this will give rise to large pressures, and even nuclear fusion can be induced. And what I was interested in is what happens when light interacts with ferroelectric materials. And today I would like to show you that our study has shown that when laser pulse is applied on ferroelectric perovskites, the light is act like a squeezer. So it squeezes along one direction and induce the polarization along other directions. And by applying this squeezing effect, we can realize the control of ferroelectric dipole moment orientations, or even induce some topological states. And to switch the polarization orientation is technically relevant. And especially when we use ultra-fast laser pulse to induce such kind of switching, because this can give rise to picosecond control of these dipole orientations. One of the most promising progress in experiments is from Professor Calaveri's group in 2017. And what they found is the following. The initial polarization is pointing upwards, and they're shooting an 18 terahertz laser pulse with the laser pulse duration is about 150 femtoseconds. And during the laser pulse, they found that this dipole moment is reversed. But you can see that the amplitude of polarization is smaller than its initial. And this reversal only exists for 0.2 picoseconds. And after the laser pulse died out, the polarization recovered back. And they call it partially and transiently reversal of the polarization. We know that in the perovskite ferroelectric materials, this so-called soft mode contributes to most of the polarization. It corresponds to the center cations moves upwards, and all those 6 oxygen anions moves downwards. This positive negative separation gives rise to the polarization. But the eigenfrequency for this mode is about 8 terahertz, and it certainly doesn't resonate with the experiment's inputs. Then what is the reversal mechanism? Indeed, there is another vibration mode around 18 terahertz. It looks like the following. It corresponds to this oxygen octahedral deformation. On the bottom and the top oxygens, they are moving upwards. And the rest of the oxygens are moving downwards. So this deforms the oxygen octahedral and causes a lot of energy penalty. And that's why the frequency is rather high. And the previously mentioned the polarization modes, let's call it P modes. This is the 8 terahertz mode I show you. In another very interesting difference between P modes and Q modes is about the contributions to the total polarization. So this is the total polarization, and the Q modes, when it condenses to ferroelectric material, the Q modes only contributes to about 10%, very small portion of the polarization. The dominant mode is the P modes. So this leads us to the question, so how exactly when we exercise this small portion of polarization, then we can reverse this dominant P modes? Why the reversal polarization is transient and partial? Can we realize full reversal of the polarization? And is it possible we can induce other types of phase transition, for instance, to rotate the polarization by, for example, 90 degrees? So before answering those questions, I would like to show you the method we use to solve these kind of problems. We use effective Hamiltonian method in Professor Blash's group. So this effective Hamiltonian model is very much like we extract the simplified basis from this first principle simulations. So the first principle considered all the rather intertwined Hamiltonian and everything coupled to each other, but we only use a selected basis from it. This is very much like we are using these sticks and blocks to build this core in this picture. And when with this much simplified model, the calculation is very will not be that heavy, and then we can simulate this light and matter interactions on real time and long real time scale and large spatial scale at finite temperature. And most importantly, since we have the access to all the interactions, we could do experimental experiments in the computer to address the corresponding interactions. So now let's come back to this PQ interaction. So in this study, this P modes, Q modes, and this inhomogeneous string and the homogeneous string are the building blocks. In our effect Hamiltonian, we have the elastic energies. We have the P modes coupled to all the strings, Q modes coupled to all the strings, and the interactions between P and Q. In total, we have 40 coefficients fitted from the DFT. We perform large-scale simulations with a supercell that contains around 8,000 atoms at finite temperature. Before the simulating the light matter interaction, the first thing we did is to validate our model. So we do Monte Carlo simulations to simulate the phase diagram of the material. We also perform a vibrational spectroscopy. So the phase diagram tells you where is this phase, where is the position of this phase at equilibrium. And this vibrational spectroscopy tells you when the system condensed into this phase and what's the vibration frequency here. Our Monte Carlo simulations has reproduced all the phase transition sequence from high temperature cubic phase goes to tetragonal phase, and then at room temperature, it will be also round peak phase and the low temperature rhombohedral phase. We have all the phase transition sequence simulated, and the phase transition temperature is comparable to the experiments. Then we studied what's the vibration frequency. For instance, at high temperature cubic phase, those peaks indicate the vibration frequency, and this black line indicates the center frequency from infrared measurements. in experiments. You can see our simulation match very well with the experiments. And then at the low temperature, the phase transition happens, the symmetry gets much lower, and those peaks subleads. And then we also have the peaks very close to the experiment's value. And when it goes to room temperature, our peaks match very well with the experiments, and the same quality when it comes to low temperature room halo phase. Then we perform the light matter interaction. We use the laser pulse centered around 18 terahertz, simulate at 240 Kelvin. The laser pulse has duration about 0.2 picoseconds. And indeed, we find out the electric dipole moments could be transiently and partially reversed. This can be seen from this red and black curve. The positive Y indicates the initial polarization. Negative Y indicates the fully reversed polarization. And you can see that this red and black curve during the laser pulse is transiently partially reversed, and after laser pulse, it's recovered back. So we would like to know what happens, what's the mechanism to give rise to this transient partial reversal. So we find that there is a biquadratic coupling terms between P and Q when they vibrate parallelly. Just to remind you that this Q mode is rather small. So this term in the energy Hamiltonian is very small. In that case, the P modes mainly vibrates in this double wire potential that have been formed by this force order to the P minus quadratic term with respect to P. The coefficient in front of this PQ interaction is positive. So when laser pulse is applied, we can see that since it's resonant with the Q modes, so Q square increases dramatically. This means this double wire potential will become shallower. And if the laser pulse is strong enough, this double wire potential could even become a single wire potential, and the P modes start to oscillate in here. And there is a chance that this P modes goes to the opposite direction, but without fully reversed. And then it's oscillate back. Then the laser pulse die out, the P modes recover back to its initial orientation. And this is called, and we summarize this effect as squeezing effect. It says when the laser pulse, the polarized direction in the laser pulse is parallel with respect to the polarization, it prefers to annihilate that polarization components. And at this mild temperature, the total polarization still want to be condensed. That's why the polarization would like to grow in another direction. And we have designed strategy to realize full reversal of the polarization by applying 3 sequences of laser pulse along 3 directions. And our numerical simulations have proved that these 3 sequences of laser pulse could reverse the polarization at room temperature. And what else can we do with a squeezing effect? How about we squeeze the material around all the directions? This will generate this we call the cubic-like phase. So the approximate value of the polarization is around 0. So it's a little bit different from the high temperature cubic phase, where the average polarization will be 0. And if we start with high temperature cubic phase, we're quenching down the temperature, then we can generate these topological defects, such as this hedgehog and vortex structure. And we can do similar things, but we do the thermal quenching effect. We have found this hedgehog and anti-hedgehog electric defects. They are the non-equilibrium states. They can survive for about 40 picoseconds. And when this defects dies out, this vortex and anti-vortex multi-domain could be formed. It's actually in a box system. It's like a vortex tube. With that, I would like to conclude. We have studied how the laser pulse interact with ferroelectric perovskites. We found out the terahertz laser pulse is like optical squeezer. It can be used to change the orientation of the polarization. It can also perform a thermal quenching effect in order to give rise to these 2D defects and 1D topological defects. Thank you very much for your attention.
We have time for questions.
Thank you for the presentation. I have a couple of questions.
Yes.
The first one, what type of molecular dynamics do you have? Do you have MDE or MDT ensemble? And the reason why I'm asking that question is because I'm thinking if heating, the local heating of the sample could play that role.
We are using MPT, and you are saying that when laser pulse applied, what effect?
Yes, if laser pulse comes, it's in principle adiabatic process. And
Yes.
the laser pulse hits the sample very much, and then you can infuse that cubic phase load, right? Because of the
Yes.
have you guys seen that?
Yes. So actually, I would say that it's a mix. So during the laser pulse, there is a large temperature fluctuation. The temperature could reach like increased 100 of Kelvin, but it's only lasts for a very short lifetime. It's about 50 femtoseconds. But then the temperature goes down very quick. So during that time, we indeed find out that there's some random orientations. It's much like high temperature cubic phase, but the dominant effect is the amplitude of these local dipole moments is squeezed to very small values. So this is what we found. It's like orientation is like randomly like a cubic, but the amplitude indeed is become much smaller. But at high temperature cubic phase, the amplitude of this local dipole moment is rather large.
But you say that there's also effect of temperature.
There is some effects of temperature for a very short lifetime, but the dominant effect is this reducing of the amplitude. Yes. Yes. It is adiabatic simulation. Right. This is so.
Thank you for the next one. I have a few questions. So I understand this lifetime suppressed polarization, but how do you reverse it and what kind of get it? So could you
Okay. So basically, okay. Okay. So the short answer is like the laser pulse change the potential energy surface. So initially it's a double wire potential, but the laser pulse has changed this double wire potential to single wire potential. And during that laser pulse, the P mode is still oscillating in a single wire potential with large amplitude. And then there's small chance that it is reversed temporarily. But when since the duration of the laser pulse is very small, then when it dies out, the polarization could go back to its initial direction. So if you just, so our other simulation shows that if you squeeze for long enough time, so instead of 200 femtoseconds, we studied 600 femtoseconds, we see that P mode is squeezed around 0 and it's oscillating there. It's instead of reversed or recovered.
Some atoms and some
Shift.
So if you have, there are cases where like offsetting of oxygen can be done by the shining light and then constant shift. Have you thought about that on any
the P and Q interaction, this back quadratic term?
And other